Okay, hope you can hear me well. So, welcome back, Shankho. And no, okay. So, let's continue our lecture on jets and associated stuff. So, today I will give you a brief overview of the subject called jet substructure. This is not anything new, being used like very popular since 2008 when the first time something called BDRS stagger, whatever that word means, and that came up, and it's one of the cases where it was born from just physics requirements and became so popular that gave birth to like conference series and going on very well for say last 16-17 years. Okay, so let's try to understand what's the physics motive. There is an echo, right? Or you can't hear echo. Okay, fine. So okay, fine. So what's the thing? Let's say we are talking about a heavy particle decaying into two lighter particle. That's always happens, and that's an interesting scenario in cases like LHC, where we are still searching for new heavy particles. So the anatomy of heavy particle decay is that if that heavy particle is at rest on our tabletop and decaying to back objects, I mean it can go any back-to-back direction, fine. But however, our anticipation is that at LHC we will, if at all we create those heavy particles or such heavy particles exist in nature, they will be created with sufficiently high boost compared to the laboratory frame, and they will decay on flight. Okay, so this is something what we expect, a boosted heavy particle decaying on flight. And if you do like class 10 level billiard ball problems, it's not hard to imagine that the decay products will be like collimated with respect to each other, and the more the initial heavy particle is boosted, the lesser will be the opening angle between these two ejected daughter particles as measured from the laboratory frame, right? So now, of course, after so many QCD lectures, I hope you are convinced that what decay we really care about are this QCD fragmentation. And this QCD fragmentation happening from heavy particle decay, if those hadrons which are coming out, we have to construct a jet, probably those particles will be confined within some angle rather than two individual jets. We will elaborate this point a bit more. So just keep this bottom picture in mind that a heavy particle is decaying, and if there are two different partons which are coming out, one carrying an energy fraction z, another carrying the rest of the energy fraction 1 minus z, then these two partons often tend to lie close to each other as long as the initial particle x is boosted enough. Now, the typical opening angle what we are talking about here is this delta r angle is twice m, where m is the mass of this particle x, over the pt of this particle x. Where this number is coming from, we will see right now. So here is the scenario again. The particle is decaying. So if you go back to the scenario where the decayed like daughter particles are almost massless, and only mass scale of the problem is the mass of the heavy particle x and the energy which these daughter particles are carrying, then you can do a simple momentum reconstruction to show that the mass square, which will be like p of this particle, the 4 momentum p of this particle plus p of this particle whole square, right, from momentum conservation. It comes out to be e squared z into 1 minus z, where this factor is coming from, because this particle is carrying a energy of z times c. This particle is carrying energy of 1 minus z times c, and if these two particles are massless, then you get the 2 into 1 minus cos theta. Similarly, if you do a little kinematics to try to figure out what this theta should be, order of magnitude, you can again show that like there will be factors of ease which will cancel out, and this number z into 1 minus z, if z is a real number, what is the maximum value of that? Okay, at z equal to half its maximum. So this is 1/4, and that 4 with the square root goes here to give this factor of 2. So that's how that 2m by pt factor comes. So that's the opening angle. Simple kinematics. So the whole point is that if you are trying to capture all the hadronic decay activities coming from decay of one single heavy particle, and if you apply a regular jet clustering algorithm with a regular jet radius parameter, it might turn out that you may not capture all of them. However, if you apply a larger radius, then you might capture all of them. So here is the like highly celebrated figure which was which came with, yes, okay.
The prong means what, like?
The prong means number of subparts inside a jet. So if a heavy particle goes to two particles which are sort of collimated, we call it two prong. If a heavy particle like top decays, a boosted top decays on flight, a top always have three prong structure. It goes to a B quark, and the associated W quark further goes to a CS bar.
So the mother particle has to be boosted to have a prong.
Yeah, so the starting point of this discussion is that we have a boosted particle which is decaying on flight. How do we capture the decay products? That's the whole underlying story of today's lecture.
So whenever like people will say about the prongs, that means there are boosted.
No, prong means how many components, subcomponents an object have. But it's not that when people say top quark has a three prong structure, it doesn't necessarily mean top quark is boosted. It means when top quark will decay, it will decay into three objects. That's number of objects it will decay to is the count of pronginess. Okay, okay, good. So now this is a very famous picture from the BDRS stagger paper. What is that? So just before LHC was switched on, people were thinking, okay, let's say we find a Higgs. Now Higgs will decay to BB bar often, right? So among the students, those who nodded yes, why when I said often? So the branching fraction of Higgs to BB bar is 58.2%. That means when Higgs interacts with other standard model particles, 58.2% of the time it will decay to a pair of B quarks. That's the highest branching fraction, that's the highest decay mode of Higgs. So Higgs often decays to a pair of B quarks, BB bar to be precise, and if the initial Higgs is boosted, then it might happen that these two B are close by each other. Now, if the radiations from these two B's are inside this larger radii cone, then if you apply a regular jet algorithm, regular in the sense that let's say this opening angle in dimensionless variables, say order of 1, whereas you apply a jet algorithm with radius 0.5, then you won't capture all the pieces of showers which are coming from the Higgs decay. So this is the sort of demonstration that you need a larger radius to capture all the decay products coming from a boosted particle. Okay, and then you need to also throw away wide angle soft radiation, because as we talked in the jet clustering algorithms, that presence of wide angle soft radiations tend to destroy the spectrum of the jets. That's inbuilt on this anti-KT distances like delta R and stuff like that. So you need to capture the larger amount of catchment area, but also you need to ensure that you throw away wide angle soft radiation, and that gave birth to the idea of large radii jets, colloquially known as fat jets. But these jets are not one jet, they should have like a few pieces of inner structure. So since we are interested in studying the inner structure of a large radii jet, this subject is called jet substructure. Okay, and that's what we are interested in, to understand what are the possible algorithms which have been tried, tested and used over last 17 years or something, which have matured and now are like industry standards, and how are their performances. That's what we want to understand today. So here is a demonstration of an event display.
So the notion of the collinear safety and IR safety is also there in jet substructure?
Absolutely. Whatever you have heard about jets, all those properties of being a good jet has to be there with jet substructure as well. Because what is jet substructure, as we will see, first you have to reconstruct a jet using jet algorithm. It's just reconstructing a jet with a larger jet radius parameter. And then once you have larger jet radius parameter, it will also eat up junks from the vicinity. So you also need to have a reliable algorithm to throw away those junks. Okay, so that's what we will learn, what is streaming, pruning, filtering, mass drop. There are plethora of such algorithms to throw away junks. We will go through the most popular ones, but this is the whole idea, that a boosted heavy particle is decaying on flight. We want to catch all the decay products in one catchment angular area, but since we are increasing the angular area to catch all the showers, we will also eat up some junk, and later we need to vomit them out. We need to clean our jets from those junks. Okay, good.
But how large is your large area?
So how large is a large area is the thumb rule 2m by pt. Okay, so that's why I said that you can do a back of the envelope calculation to see how this number comes. I mean, that's not a hard and fast number. The origin of this number 2 is where this function 1 by square root z into 1 minus z picks up, and that's it. I mean, now if you ask, does it guarantee if I choose the radii of the jet exactly to be 2m by pt, I will catch all the shower fragments originating from a boosted jet? No one can. It's a stochastic process. It's a quantum mechanical evolution. So no one can guarantee that. But the thumb rule is that if you choose this radius, more often than not, you catch all the showers so that the jet spectrum is undistorted. The PT, the mass, all this parameters.
I'm worried because if it is of the order of lambda 1 by lambda QCD, then of course you will see nothing.
So delta R has to be then lambda QCD by PT. I mean, delta R is a dimensionless object. So then, but given the amount of boost we are talking about, PT is quite large. If a jet is that large PT and lambda QCD is 200 MeV, that's not where we are interested in applying these algorithms, right? So that's the scenario. We are not worried about lambda QCD when we are talking about boosted jets.
So this 2m over pt, like to know the 2m or pt, you have to construct the jets. And even like to construct the jet, you have to know that delta R. So how do you perform that?
No, so that's where we take help of simulations. If we are anticipating a particle of certain mass and we want to deploy a jet algorithm to catch the fragments of that heavy particle, then our simulation will tell us how will be the angular distribution as a function of pt. In fact, I must have a plot like this. So here is the plot from simulation, that this is the plot for a boosted top quark decay, and you can see that when we know the top mass, given the boost, the transverse momentum of the original top quark, what is the delta R, optimal delta R to choose, so that you capture statistically maximum amount of the particle. Okay, so this is a simulation driven study to optimize what is the exact jet algorithm which should work well, given you a priori have an idea what is the kind of mass of the original resonance you are looking for.
So anticipated mass you can predict, but the PT actually it can vary. So
yeah, sure. So once you choose a mass, then you can vary PT and can make this simulation plot, and then can pick up a delta R and then go back to the laboratory. So this is the scan, exactly the scan you are asking for, that what delta R I should choose. So what goes in to make this plot? I know the mass of top quark, 173 GeV. Now I see that if the top is boosted, what should be the optimal value of delta R so that I catch the hotspot, right? So here in the simulation, they sort of started with something like 750 GeV top quark and found from the numerical simulation that delta R between the W and bottom is the subjet mutual angle should be around 0.4.
So you take the minimum PT.
No, I take the PT where I want to operate my machine, where I want to do the experiment, what is the phase space which I want to probe. That will determine what PT I am looking in.
Then delta R will be dynamical even where.
I mean, initially you can put constant, but people do talk about dynamical radius jet, variable radius jet. I mean, he has written a paper on variable radius jet. We have worked on this from almost 10 years now in the experiments on variable radius jet, so on and so forth. Okay, good. Let's go back to where we were. So here it's a demonstration from an detector event display that when a boosted top decays and deposits their energy in the calorimeter, how it looks like. So you can see the three-prong structure clearly visible from the cell deposits which we captured, and here you can see that the three-prong structure individually shown. Here is the highest amount of energy deposition. So the takeaway, selling point of this figure is that if you choose small radius circles here, you will never capture all the decay products coming from the top. Whereas if you choose a larger radius, you will end up catching all the decay products. But not only that, you will end up eating these red points as well, because their presence in the vicinity. Those are the junks which are there, called pileups, and there can be other beam remnants and stuff like that. So if you increase the radius of the jet, they will also appear. Now if you count them to compute the spectrum of the distribution which you are interested in, of course presence of those red spots will distort your spectrum. Okay, so somehow or other you need to get rid of them, and one of the highest amount of activity went on in our field for last 10-12 years to develop algorithms to how to get rid of those chunks which are eaten up by large radius jet. Good. Sorry?
What are those green lines?
So those are the track deposits, and then there are other deposits from ECAL. So the green lines were the components of charged energy contributions there. The blue ones are the calorimeter, okay, the ECAL and HCAL deposits. The green ones are the tracks, and then the red ones are the junks, right? Good. So here then became one of the major question. I want to tag Higgs because I'm interested in studying Higgs. Higgs decays to a BB bar, but something else also splits into a BB bar, which is a gluon. There is a prompt gluon coming from QCD radiation, which decays to a BB bar, and if you compute the mass of this gluon to BB bar splitting, you will find there is a finite mass. So just by putting a mass threshold, you may not reject all the QCD background originating when you are studying Higgs. So now how do you develop your algorithm to just throw away the QCD background? Okay. So before going in, here is one of the event display of a boosted top decay inside Atlas calorimeter. So you can see clearly from the the distribution of the energies, the depositions of the energies, how close by the energy deposits are when you apply a jet reconstruction algorithm on them, and the red line is a muon and things like that. So it's not just that only simulation shows up what we want to see. Actually, in real life, these things are every now and then pops up, and we need to understand them. So here are the stuff, what is what. So you can see this is sort of a TT bar event where you have the one of the top in this direction, then there is mate, muon, and all this stuff. Okay, so we measure all these little pieces of energy what you see, and we have to reconstruct them. Great. So now what is the zeroth thing you can measure? It's the jet mass. Now in today's slide I decided that I won't give you theoretical formula for all the taggers, because what I realized that when I show them, it's just some formula appearing in front of you for 10 seconds, it's going away, and let's be realistic, they just don't stick with you. So the way I will develop today's slides are more intuitive, like I will tell you what is the underlying intuition which is going beneath the construction of the taggers, but just to show that everything what I am going to show you has an explanation through perturbative QCD. So for the jet mass, I will show you what kind of calculation goes on. Similarly, jet PT, jet charge, etc. Everything has fixed order perturbative calculation with relevant resum parameters. So what when people compute jet mass, they tend to construct distribution of this quantity where this V is the mass of the jet square by energy of the jet square, and you see that here are the order of alpha s contribution, order of alpha s square contribution, and this is in the small v limit of course, and these numbers are like the CF and all this stuff. Okay, so just to show you that if you plot a differential distribution of jet mass, it has a prediction in perturbative QCD. But this is the first and last set of equations I am trying to show you today, because in the first two lectures when we were doing Q bar G and things like that, those were simpler in the sense that even with the 10-15 minutes of slides, I could show you the exact calculation. These are much more involved, and if you start going through these calculations, and then one whole talk will go away in computing one or two variables. So that's not point of these lectures. I will later put exact link to the sources of this, and you can see the calculations yourself. So what I want to then show that when we talk about jet mass is relatively simpler thing when we are talking about experiments. In experiment, what we call jet mass is a thing like following. So I have a jet which has constituents, each have a 4 momentum pi mu, and the jet 4 momentum by definition is a sum over I pi mu, and thus my jet mass square is p mu p mu. Okay, this is very simple definition. But when I showed you the previous slide, the definitions of how to compute them from perturbative QCD, probably you saw that there are alpha s powers involved and logs involved, and it's complicated. But nonetheless, these distributions you can measure and also can predict the computation, and you see the level of agreements. So here is the total data in some TT bar event, and what will be the TT bar production can be like computed for each of these different processes, where in theory you can compute them from TT bar event, single top event, W plus jets event, etc., etc. So when you stack them up, you see there is a sort of amazing matching between the data and the summed over all the theory calculations, which says that our fixed order perturbative QCD understanding of jet mass and what we separately parallelly compute using this piece of definition are quite in good agreement of each other, and this is an experimental verification of that fact. Okay, so we understand the individual jet observables, jet mass, jet charge, all other measurable quantities which you can think of related to jet, those can be computed using the methods of perturbative QCD. But jet mass itself is a nice dagger itself, because if you are looking for some background for Higgs or background for boosted top production, then itself if you construct the mass of the large radius jet, then you will see that most of the cases the background combinations are falling far away from the resonance mass, and the resonance mass is picking up. Now, in general, when we are talking about substructure, what we try to do is a general class called pronginess finder, which I already explained. Like if you have a Higgs to BB decay, it will be 2 prong, a top decay will be 3 prong, so on and so forth. Another one is the groomers. Yeah. Which one?
The previous one.
This
plot.
one.
Previous plot, yeah. Here you do not consider any heavy particle decay.
Top is a heavy particle, the heaviest particle we know of.
When you say the zeroth jet substructure, so you do not consider any heavy particle decay?
No, sorry, I didn't get your question.
So zeroth jet substructure means there is no substructure.
You see something called trimmed R equal to 1.0 anti-kT. Trimming is an algorithm related to jet substructure, which means there were jets deconstructed with the jet radius parameter 1.0. Then trimming means there were soft particles. I will come to explain what is trimming, but naively there are soft particles in that jet, and you have an algorithm to identify and throw away those soft particles. That's trimming. A parallel family of like jet groomers called pruning, soft drop, etc., etc. So when you see this plot, of course there are some jet substructure methods which went in.
And zeroth means?
Which one is zero?
In your caption, like jet mass zeroth substructure, what is the zeroth means?
Zeroth jet substructure, which means the first one. Huh?
I'm not getting actually.
Don't worry, 0 is a label. What I want to say is the mass of a jet, of a filtered large radius jet, is a well understood quantity. Okay, good. Okay, we covered this, and then this is what we will be again talking about, the general class of filtering methods, trimming, pruning, general called grooming. So what's the idea? There is a large radius jet, and you have its constituents, which is a mixture of genuine hard particle radiation and also contamination from soft particles like pileup, underlying event, so on and so forth. So how do you identify those soft particles? The algorithm is go back to the constituents and start reclustering jets with small radius jets. Now, if you apply small radius and almost make circular jets or other KT jets, it will identify. Now remember, the KT algorithm we demonstrated is very much sensitive to soft particle emission. It captures the soft particles. So it will clearly, with this small radius, will identify which will be the radiations coming from hard particle and which are the energy deposits coming from soft particle. And once you have reclustered these small pieces of jets, then if you have through KT algorithm identified the soft particles, then just throw them away. So this is what it shows, that after identification of all this, this algorithm found that all these gray blobs are originating from lump of soft particles. So those were thrown away, and after this dressing, what is left are these 3 isolated blobs, which are supposed to be 3 different subjects of a top quark. Okay, so this is like a demonstration. It's a cartoon demonstration to demonstrate how this algorithm works. Now, another concept we need to keep in mind while evaluating the performance of the taggers is something called receiver operator characteristics, or something called ROC curve. So ROC curve says, like, always if you define a filter, a cut, some background will pass that cut. There is no ideal tagger in life which can in reality only select the good stuff for you and can reject the bad stuff for you. So if it's known that whatever way you choose a filter, some bad stuff will peep in, then how do I evaluate the filter which I have made, the filter which I have constructed is performing best? So what you do is choose a working point for these taggers, you choose a cut value for these filters and compute what is the signal efficiency for that cut value and what is the background fake rate for that cut value, and you slide that cut value. So for each choice of that cut value, you will have a different estimation of signal efficiency and a different estimation of background efficiency. So you slide the cut value and make this contour. So if you don't have any idea of whether a choice is good or bad, so it's like tossing an arbitrary coin and the outcome is 50-50, then you lie on this diagonal line, that you always have equal amount of signal efficiency and background efficiency. However, now if you put a smart filter, then for a given choice of background efficiency, you will tend to increase your signal efficiency, right? So an ideal tagger should take you to this bottom right corner where your signal efficiency is +1, background efficiency is 0. That's never the reality. So the better and better tagger you make, you sort to like lie on a ROC curve which is going in this direction. So the red, if you get a tagger 1 which gives you a ROC curve of the red one versus a tagger 2 which gives you a ROC curve of the blue one, you say my tagger 2 is better, because for the same background efficiency you get better signal efficiency, right? So remember this picture, it's just conceptually important. Now we will also look into methods called pile-up mitigation. So what is pile-up mitigation? We already talked about this once, but you know there are secondary vertices which get created. So in the reconstructed jets, there are contribution from pile-up, and then we at best can identify the charged pile-ups because we can take help of the tracks, etc. But neutral pile-up is very hard to remove. They tend to stay with us. So here, like this is a cartoon of how pile-up removal works in concept, and there are different methods called charged hadron subtraction, pile-up per particle removal, etc. So here is a diagram which says that, look, originally I had a jet which had my basic raw particle flow constituents, all the blobs, which was contaminated by pile-up. Now I applied pile-up removal. So my jet energy resolution at low PT, where the effect of pile-up is most, there it improved. The lower the value here, it means the jet energy resolution is better. And in low PT, when you apply on the jet all these pileup removal techniques, the jet energy resolution got better. Okay, so this kind of things, what I'm telling you conceptually at a broader level, this kind of things work pretty well. Now, how these things actually work, you have to do it. Otherwise, it's hard to explain the algorithm in 2 minutes. Yes. Yes.
So, pile-up removal or pile-up like subtraction, like how different is the algorithm when it comes to fat jets versus?
No, it's almost same.
It's almost the same.
Yeah.
And I'm also curious. First of all, why do we observe better jet energy resolution for low PT versus high PT?
No.
And
no,
why are we constrained within this pseudo rapidity range of 0.5?
No. Okay, good questions. First of all, we observe better jet energy resolution at high PT because when we go down, that's what is better. The resolution, the more the resolution, that means that's the amount of the uncertainty, right? So when we apply that here in the low PT region where the dominance of pileup is most, after application of this pileup removal algorithm, the resolution went down, that's actually better. That actually shows it works. Now your second question was like why it goes down at higher energy.
Why do we constrain ourselves within pseudo rapidity of less than 0.5?
So that's the barrel region, what we colloquially call. That's where the calorimeter resolutions are best. Okay. So
this algorithm will not work at higher.
it will work.
It will work. Okay.
It's just a demo. Like if you see a public plot, a public page, you will find plots for 0.5 to 1, 1 to 1.5, so on and so forth, up to 2.5.
And these are different algorithms like particle flow and.
No, particle flow is the like mother algorithm is just how you construct all the stable constituents. Now on top of that, you apply a pileup removal step, which is charge hadron subtraction. Another parallel candidate is pileup per particle, which is PUPPY. So these two lines, the red and the blue, is a comparison of the performance between charge hadron subtraction and PUPPY.
Okay, thanks.
Yeah. Yeah, Dipanshu.
Our formula was for the radius r, the 2m by pt, but here the radius is fixed in the algorithm, the 0.8. So
Yeah, but like here we don't know what mass we are looking into. This is like in experiment, if the regular radius is 0.5 for regular jet, you need to choose a radius for large radius jet, right? Now you could have chosen it to be 1, 1.2, 1.5. Remember, the more you increase the radius of the jet, more and more you are contaminated by the pileup. So the collaborations have done enough amount of study to freeze in on a value of the large radius jet, that what radius gives the physics performance okay, but still not too much contaminated by pileup, so on and so forth, and they zeroed down and settled on a value of 0.8.
the second question was related to this, that you are saying that pileup dominance is most at lower PTs.
Right.
Is that because then the jet radius is larger?
No, the jet radius is fixed.
Right.
It's just the like given like an opening, a solid angle, there most of the hard particles are coming from primary vertex. The wide angle soft radiations which sort of flown away from the secondary vertex but landed up in this jet, those are by construction soft, because since if they were not soft, they wouldn't have flown in this wide angle radiation. So pileup particles are soft. When you hear this folklore, it's because those are this wide angle radiation from secondary vertices which landed up in these jets. Okay, so that's why those are soft particles. Good. So here, like whatever I was talking about, trimming, pruning, filtering, there are many of them. There is no point in going through every piece of them which are sort of identical, but here is the whole idea that once you want to like filter your stuff. Like it's like you have a bag of stuff in which there are junk. You open the bag, find out piece by piece which are possibly junk, take them away and throw away. So this is like, again, you recluster the constituents of a large radius jet and figure out which are the real hard element, which are the soft element, throw away the soft element. So this is how the trimming, filtering, pruning, soft drop, etc. works. So I will now go through some of these algorithms which are very well measured, unified across experiments, and which are used day in, day out for real life measurements and searches. One is the mass drop. So mass drop is the BDRS stagger, which tries to define a distance metric like this, and you may find this familiar because when in defining jet algorithms in the previous lecture, we were talking about some numbers like Yij, which is less than Y cut and stuff like those. This is exactly that algorithms, that you put some like cut on the Y, and there is also a cut put on how the jet mass will be split, so on and so forth, and you filter out the jet, you throw away some junks. Similarly, there is something called trimming. This is something we already discussed about, that the reclustered subjet, if they are carrying a total PT fraction smaller than a number, you identify them as the reclustering of softer particles and you tend to throw them away. And finally, pruning is like what is the subjet PT over the total jet. So again, those are symmetric splits. Now you can see when I show all the definitions of this jet groomers that lots and lots of parameters which goes on, and no one exactly knows which choices of parameters will work best. So what you do in that case, you scan over the values of the parameters, test them in real life data to check that what choices should work well. And that what was done by the experiments for last 10 years to zero down, and this is the demonstration. So after you apply all these methods, you need to verify that your ultimate goal is that those chunks which were sitting inside jets, if they were removed, then your jet mass resolution should become better, and if at all that's the case. So this is a demonstration that one had a R equal to 1.2 jet, one applied some filtering, etc. This is on a simulation of boosted Z going to QQ bar, and you can see how much is the improvement on the mass resolution. The dashed ones is before any grooming was applied, the solid one is after the grooming was applied, and you can see the peak around Z mass, 90 GeV became so much prominent. And also this is something about pileup removal effect. Okay, so here the like F cut, it's the trimming method, this F cut parameter method, which is applied for pileup removal, and when the pileup, the reconstructed vertex went up, the amount of pileup increased, so the jet mass kept increasing because the jet was eating more and more soft chunk. But once you remove the pileup, you can see with a number of pileup increment, the jet mass became stable. So this is again a demonstration that this grooming and filtering methods tend to work quite well. Okay, great. This is another plot which we the experimentalist always ensure to reproduce from raw data, that we talked about large radius jet, but we need to ensure what we are calling jet in experiment does make a sense, and we make it happen by producing something called jet energy scale plot. What does this mean? This plot says that over a wide range of 200 GeV to 2 TeV, if we have reconstruct a large radius jet with any of value of the PT, then we know the jet for momentum within an uncertainty of this much. So at low PT, which in this case is 200 GeV, the maximum uncertainty on the reconstructed jet PT is 6%, whereas it drops to something like order of 2%, and again it increases to maybe 2.5%. So that's a remarkable thing. Like over a wide range of PT, we reconstruct these jets, and when we compute an observable, if you ask me that how do you know you have done a good job, or how do you estimate how bad you have done, I will go and say, look, I can guarantee you what I am doing can at most have an uncertainty of 6%, not more than that. Okay, so that's a decent number given the complex systems which we are dealing with. Yeah.
This JES uncertainty, this is for the large radius set, right? R equal to 1.0, right? And what about this indicative 0.4? What is that?
No, so these are normally done with tag and probe method. Okay, so here it says we had a large radius jet, but what in the barrel region we use for the tag is an R.0.4 jet, whose jet energy scale we know even better than this scale, like here 6%, 2%. For that 0.4 jet, we know the momentum uncertainty at much higher accuracy level. So that's what we take as a standard candle. With that, we recoil this jet and try to measure how much we know the momentum uncertainty on this candidate.
And another is that what is, so this behavior tells that this is higher on the left side and let's say JES and
I mean, say low PT and high PT.
high PT, yes. Low PT and high PT, and there is a dip. So do you understand the behavior?
Yeah, so at any point of time, if you see from where the most of the uncertainty is coming from, you see that all through the highest amount of like uncertainty is from the how well we know 0.4 jet, which we were recoiling against. Then you can ask, oh, but for even 0.4 jet, why the low PT is higher? And low PT is higher mostly due to pileup. Okay, because pileup is the most dominant source at low PT. But then there are other thing as well. And now what happens that at intermediate energy, the calorimeter starts taking up, but in computing jet PT, a large amount of contribution is given by the tracks, because 65% of jet energy comes from charged pions. Now if you go to high PT, then tracker loses its resolution. We can't take help of tracker at all. So that's why again there you see a small tend to rise. That's because no track component is contributing there, and again our uncertainty on the momentum estimates goes higher. Okay, so there's a very good reason why this plot follows this pattern. Good.
Okay, thank you.
Now, what we want to show that although we are talking big things about grooming, etc., for a lot of time, that's not sufficient. And this is just shown through again another simulation that shower pattern itself of QCD can replicate a three-prong structure. Okay, and in that case, a groomer will fail to identify or a top jet versus a QCD radiation, and in that case, you need to introduce energy scale dependent quantities. So jet mass was one of them. Then there are dimensionful quantities like KT splitting scales. So remember, this is always done like you have a jet, go back to last iteration of the combination, recombination of the jets, and keep computing them. And then we have this famous observable called N subjettiness. N subjettiness is something, it tries to determine whether a boosted heavy resonance is how many different subcomponent it has. Like for a top jet, it will discriminate between three-prong structure versus two-prong, or three-prong versus one-prong structure. Similarly, for W tagging, it will try to identify two-prong structure versus one-prong structure, so on and so forth. Okay, So let's try to see how, like given this jet substructure methods, how well do we know these cases. So here again the top jet and QCD jet radiation, then I apply different amount of tau 32. Okay, so you see that for the similar structure, what is the tau 32 value is coming from top jet and QCD jets, and then the takeaway message that a true three-prong structure has lower values of tau 32 compared to a background. So that's what we will use as discriminator. So it's just a table that what are the kind of values which we choose while we design a tagger in real life to make things work, to identify a boosted Higgs, a boosted top, so on and so forth. And these are the performances. The performance is what? Look at these individual quantities that we build up something called KT splitting scale and N subjettiness and so on and so forth. So this is the KT splitting scale of D12. And although these are sort of complex objects, for a boosted top scenario and boosted W scenario, this is boosted top essentially. This was from 8 TeV. I'm showing some old plots, but nonetheless it carries the same message that you can see where the tau 32 is picking up and where the KT splitting scales are picking up. And the most interesting thing is all this process, the KT splitting scale, etc., for different Monte Carlo, which are different physics process, will pick up at different places. But nonetheless, when you add all the different standard model processes, the envelope of the data gets recreated so that the ratio is close to 1. So that says that in data at different kinematic regimes, we really have good understanding of these different jet substructure variables. And we keep on calibrating these jet substructure variables. We tend to use them for measurements, for search, but this is the testimony that across different regimes of phase space, across different physics processes, we do understand them quite well. Okay. I will go through a little detail of something which was and is very popular over the last 10 years, something called HEP-top tagger, and it became one of the most popular for identifying large radius jet. So the way it worked, that at first step, given a large radius jet, you just do a mass drop decomposition. So you throw away the soft particle, then you do some iteration. You keep clustering them and always try to form 3 subjet combination. And on this combination, you do reclustering with like filtering, okay? And you try to repeat this process one after another, so to ensure you throw away all the soft particles. And this iterative algorithm showed that you tend to reconstruct a jet best, like large radius jet best, in data when there are high contamination with pileup. This is the performance of HEP-top tagger, that in data it sort of figured out a good top candidate with pretty high degree of efficiency, and it works. So we can rely whatever jet substructure methods we are talking about building, etc., that even it works in the data pretty well, which is very, very essential to ensure that it's good for precision measurement as well as searches. Okay, good. So this is the PT. Just this is the larger jet mass. This is the larger jet PT, and you see that even for single top TT bar, etc., we have a good like understanding of the top PT, the reconstructed large radius jet PT. Good. Now, like, of course, given that you have all these 20 possible, yeah.
So in the previous plot, yes, this one, the top quark jet mass, it always seems to have an asymmetry on the left side. So is there a particular reason why it's not a Gaussian-like thing and it always has a tail near 120 and 100?
Yeah. I mean, first of all, when there are real life energy loss, the nature of energy loss in the detectors, they are not symmetric, they are asymmetric. So that's why jet mass resolution, if you plot what is the true jet mass, the reconstructed jet mass over true jet mass, you will find non-Gaussian tails. And that's because the hadronic shower deposition in a calorimeter is actually, it actually has asymmetric response and have a tail in lower side. That's what getting reflected in this plot itself, that there are real life energy loss when the hadronic shower is entering in the hadronic calorimeter, and we can't reconstruct them.
Okay, thank you.
Yeah. Good. So, yeah.
It goes as W and a bottom quark, and the W to two other quarks. So the boost factor is
So-
not equally distributed, and so is the energy. So that
Yeah.
would also introduce bias.
Right, and let's say the nature of the way the showers of a heavy flavor deposits energy versus light flavor, there is
Exactly. So
asymmetry.
there are many things at play.
And also, when the boost is extreme, it may be the case that the calorimeter cannot stop the particle. So there is higher amount of energy leakage, and if there is energy leakage, then there is no point, you just can't reconstruct the invariant mass, right? Yeah. So all the factors are there in real life. Good. Fine. So here we were comparing all the different taggers on the rock curves. Okay, just it's the efficiency versus rejection, which is the reciprocal of efficiency. So here you can see that given all these taggers which we defined, so on and so forth, how do they perform, how much top tagging efficiency they can reach, and all these blobs which you see on the plots, those were the working points for individual taggers, and choosing a working point is important in experiment because given a working point you will calibrate the tagger and then deploy in general measurements and searches. So it's you just don't scan over all the points on a rock curve, you choose a point and keep fixed, you keep yourself fixed to that point. So finally, I will talk a little bit about Higgs tagging algorithm, which is of course our starting point motivation, which was for today. So here you can see that in calorimeter, like in a real life event display, what will be the nature of energy deposition coming from a Higgs to BB part decay. So in the track there will be two tracks, and here it comes that depending on the boost we apply a variable radius clustering algorithm, and finally on this large radius jet we try to figure out what are the two subjets, and accordingly we try to make a symmetric splitting. Okay. So these are the Higgs taggers which we have, and here are the performance of the Higgs taggers. So when we have let's say 70% Higgs tagging efficiency, it's the 10 is rejection, that means 10% is the background contamination. So these are the kind of performance we have for the taggers. Now all these things are right now done using machine learning. I thought in one lecture I won't dump you all the machine learning stuff with this stuff. So here today I ensured that you get exposed to the language of boosted jet, the substructure, the taggers, and in tomorrow's lecture I will try to introduce you where machine learning creeps in this picture and then how they are used in the context of jets. And so tomorrow probably I will take a little more time, maybe 15-20 more minutes. I think Professor Haridas is done. So tomorrow I may take up like a little more time. So I will just cover some basic introduction to the language of machine learning and then how they play their role in the tagging substructure, etc. in the context of jets. Okay. So that's it. I will finish it today. I won't dump more stuff today. So tomorrow we will start with a fresh language and try to converge with whatever I talked today. So yeah, thank you. So if you have questions, since we have some time today, 10-15 more minutes, we can go through.
Excuse me. I have a question. So, some general question like, let's say when you compute the QCD corrections, so how do you incorporate all this grooming, pruning, and all this stuff with respect to QCD computations?
No,
So let's.
every
I want to just add one more line. Let's say for KT algorithm and anti-KT algorithm. For the jets, we can apply the same algorithm for the QCD computations, and we can check actually whether infrared and collinear those are cancelling properly with respect to the jet definitions. But when let's say if I think about all these more cutting edge technologies techniques, so how do I incorporate the QCD computations with this?
All this trimming, pruning, etc. will give you which region of the phase space inside the jet you're keeping versus what you're throwing away. So now you look. I think I'm almost sure, but there can be little mistake. But I think for that region you recompute using perturbative QCD. Like as I said, for the mass, I showed you how the calculation goes. Now I can show you again, like for each tagger, how do you compute that differential cross section for those groomed quantities using the methods of perturbative QCD. So there was a quantity called 1 by sigma d sigma dx, where initially we showed it for x is jet mass square by jet energy square. Similarly, that x can be some groomed observable over the corresponding dimensionless combination and can be computed using perturbative QCD. I mean, yeah.
Okay, we can discuss later. Not clear to me.
Sure, but like for every choice of this tagger, etc., there is a way to compute the differential distribution. Okay, so 1 by sigma d sigma dx, where x is the groomed quantity, you can compute in fixed order perturbative QCD exactly, not exactly, through perturbative QCD. So it's there in the literature. Yeah, I mean, whatever I showed you, like trimming, end subjettiness, etc. Like even in 2013 already there was a big paper by Mrinal Dasgupta and company that how do you tackle this jet substructure observable starting from perturbative QCD. Recently there were papers on for heavy flavored jets when you look substructure, how do you do the QCD computations? And for different collider scenarios, computing them for lepton colliders, computing them for hadron colliders, people try all this. I mean, there are results.
Sanmay?
Yeah.
So initially the BDRS algorithm was developed for the Higgs to BB bar.
Right.
So could you just remind me, I probably forgot, what is the reason that we consider the radiation from one of the, like we consider finally at most three subjects, like radiation coming from one of the bees and not both of them?
No, I think both of them is one higher order QCD computation which people were not.
It's the QCD order that's we are sticking.
Yeah,
with.
yeah.
Okay.
So and the people tried that because people already knew what's the result for Q bar G, which we are talking
Right.
about.
Yeah.
So they can just plug in that result.
Okay.
Yeah.
So since we have time, I will ask you another question. So there is this energy momentum tensor deposition and all to characterize jets. Can you explain that?
No, so the thing is, first of all, from an experimental point of view, what you can measure when you talk about jets, let's say these are my eta phi segments of the calorimeter, and you get some energy deposits inside a jet, right? So you know for each cell the amount of energy and the location of the cell itself. So for an ith cell, you have three pieces of information: EI, eta I, phi I. And now you like by hand impose that those individual cells are massless. Those are like null components. So then you have a zero mass particle with energy EI, eta I, phi I. So you have four vector for each energy cells, and then you feed that to jet clustering algorithm. Yeah.
The grooming happens in a similar manner.
So grooming happens like
You
once
do now energy threshold because you leave some of the soft part.
yeah, so that happens to this F cart and stuff like that. So here if I see this picture, so what happens is that I have a jet which had lots of small components, original jet components. Now you form small radius subjects, so on and so forth. Now each of this individual subject has a PT. Now if the subject, ith subject PT of I over the actual jet PT, which is of this whole big jet, is less than some threshold fraction called F cut. That means this particular cluster, whatever particles they were carrying, they are soft particles likely to have originated from PILAB. So you just throw away this subcombination absolutely. Okay, so that's the way the algorithm flows, that you recombine all the constituents but smaller radius jet, so that you try to identify within this big circle if there are geometric patches which were contaminated by softer radiations, and you want to.
And then your radius also shrinks.
No,
No?
radius remains as it is.
Remains same.
Yeah.
Just so when you look at the final
Let's say I want to use
signal,
the final jet.
then
I have the same original jet radius. I have thrown away few constituents
okay.
which were originally there. So this is the dressing method. I want to get rid of some constituents because I know they are not the true ones which I am looking for.
I had one question. Maybe.
So let switch on the microphone.
So it does not become relevant anymore. So that radius you just started with, and then
Correct.
you
That's
don't
correct.
use it anymore.
So now all you care are the good candidates, and that's it.
Yes, so on the last plot that you showed for the Higgs stagger, you go to that once. Yes, so why is a single B being tagged here?
So, sorry, why?
So there is the single B tagging written in the legend of the plot.
Oh, so that means ideally there should be two B jets inside a boosted Higgs. So you have found two subjects, but you are selecting them by requiring at least one of them should have been B tagged. Why? Because typically if you take 70% as the B tagging efficiency, if you do double B tag, then it becomes 49%. So you throw away lots of jets. So instead of doing that, you say, oh, my two-prong jet almost looks like Higgs, and instead of ensuring both the subjects are B jets, I will just make sure one of them is B jet, just to increase the selection efficiency.
Okay, but suppose there is a boosted Z which can also go to BB bar. So does this algorithm fare well in determining whether it's a Z or a Higgs?
No, I mean that will pick up the quantity, but then you have to combine with mass and other taggers as well.
Because the mass window will also cover the Z mass, right? It's 76 to 146, so Z
Right,
is
right,
76
right.
to
So
100 maybe.
I mean that's why there is a like here it's only Higgs versus QCD jet rejection and top jet rejection, but there is another plot for like electroweak rejection.
Okay,
Yeah,
thank you.
yeah. I know this is mostly simulation driven. That given you know the pile-up environment where you will work with, then you run through realistic simulation and try to figure out how you optimize your F cut so that your jet energy response is good enough.
Also, to add to Juhi's question, for the Higgs mass here, why do we keep, like, I know that it's much broader for a fat jet, but why do we keep such, like, again, it's asymmetric because of that reason, right? Like, we have 20 GeV on the
You
right
saw
side.
so I mean that's like almost you can read out the number as what is the width where you like cover 3 sigma of the curve, like let's say 95% of the curve of the signal. Yeah, that's how you define this range.
But single B subject tagging versus double B subject tagging won't help the Z case, right? Because Z to BB bar will also have that. So we definitely gain by having
Yeah. And
single
also
BZ.
whenever we talk about B, you should always remember light can fake as a B and
Yeah.
C can fake as a B, all this stuff.
Which are also momentum and rapidity dependent quantities.
Of
It's
course,
not a constant.
all like in real life in detectors, whenever we make a statement, every performance have to be binned in rapidity and phase space region.